Hi class, welcome to your first lecture on chapter 12. We'll talk about circles and other conic sections. In this section, we'll start in section 12.1, which is circle review and tangent lines. So now we only have two objectives in this section, and that's to review circles and arcs and to use the properties of a tangent line to a circle. Now, while there's only two objectives in this lecture is going to be on the longer side. So let's jump right into it. All right, first off, in a plane, a circle is a set of all points equidistant from a given point called the center. So you have a center, and then we know what a circle looks like, but the circle is really just a set of an infinite number of points that all are equidistant from the center. So the diameter is a segment that contains, so a segment is kind of like a line, remember, contains the center of a circle and has both endpoints on the circle. All right, the length of the segment is also called the diameter. And then a radius is a segment that has one endpoint on the center and another endpoint on the circle. So the length of this segment is also called the radius. So, just kind of like looking here, AB here is what I talk about as the diameter, all right? It's a line that goes through the center, all right? And PC here, okay, that's a radius because it has a line that goes from the center all the way to the edge of the circle. All right, so congruent circles have congruent radii, right, or all the radiuses are the same. Now a central angle, right, you'll notice here that I have some angle measure, is an angle whose vertex is the center of the circle. Okay, so the center of the circle contains the vertex of the angle. That's called a central angle. All right, so now I want to talk about arcs. So arcs are specific components of a circle, okay? So a semicircle, all right, is half of a circle. So you can see right here, this would be half. So a minor arc is smaller than a semicircle. So this arc here, RS, notice the notation arc RS is a minor arc because it's less than half the circle. And then this arc, STR, so all the way like this, all right, that right there is what we call a major arc, right, because it's larger than a semicircle. Right, so minor arc, smaller than half the circle. Major arcs are larger than half the circle. All right, so let's talk about some arc measures. So a minor arc, the measure of a minor arc is equal to the measure of the corresponding central angle. All right, so what I'm saying here is that the measure of this arc is equal to the measure of the corresponding central angle. And the major arc, right, the measure of a major arc is the measure of the related minor arc subtracted from 360. So it's the leftover part. And just kind of remember for a semicircle, the measure of a semicircle is 180 degrees. All right, now unfortunately this didn't come up in the PowerPoint, so forgive it. But this is saying the measure of arc, RT, is equal to the measure of this angle. So the measure of this arc is 50 degrees. Now the measure of arc, so this is not coming up, but it should be an arc sign here. The measure of arc TQR is equal to 360 minus the remaining. So the measure of arc RT, so 360 minus 50 gets me 310 degrees. All right, some other things. Coplanar circles have the same center, are what we call concentric circles. All right, so these two right here are concentric circles because they have the same center. And the measure of an arc is in degrees, while the arc length is a function of the circle's circumference. So the measure of an arc is in degrees, remember that, but the arc length is different, right? And that's a measure of the circumference. And circumference is the total distance around a circle. All right, so here's a theorem for arc length. The length of an arc, which is different than arc measure, I know that seems weird, but the length of an arc of a circle is the product of the ratio of the measure of the arc, which is the angle, divided by 360 degrees, and the circumference of the circle. So the measure of this arc AB is equal to whatever the measure of this angle is, really, divided by 360 degrees times 2 pi r, or the same thing times pi times the diameter. Same thing there. All right, let's work an example, or let's move on to talk about congruent arcs, and we'll get to examples in a second. So congruent arcs are arcs that have the same measure and are in the same circle or in congruent circles. So what we're saying here, if circle, forgive this for not showing up, if circle O and circle P are the same, then the measure of arc XY is measure of RS. All right, it is possible for two arcs of different circles to have the same measure but different lengths, okay, because they're going to have the same degree but different lengths. It's also possible for two arcs of different circles to have the same length but different measures. Like if you look over here, these two, all right, have the same measure. These arcs are each 45 degrees, but they have different lengths. So the measure, all right, of arc XY is not equal to the measure, all right, of the length of arc AC. And it's the same thing here. They have the same length of these two arcs, but different measures, okay, because they have different angles. All right, so we're saying here that arc XY is not congruent to arc AC. So remember, they need to have the same measure and the same length for them to be congruent. All right, so a little bit on. Arcs are not congruent. All right, they can have the same measure, but not same or congruent circles or different lengths like we see here. And these arcs are not congruent. They have the same lengths, right, but not the same or congruent circles, so different measures. Right, so they need to have the same measure and the same length for the arcs to be congruent. Remember that, same measure, same length. All right, now forgive these typos. All right, these are for, there's supposed to be the arc sign above these here. All right, so I have this circle at radius O. I want to find the measure of arc BE, so from here to here. I want to find the measure of arc AED, so AED all the way around. And I want to find the length, okay, the length of arc DEF. All right, so let's do the solution of measure of angle B to E. Well, that's equal to the measure of angle BA plus AE. Well, I know what BA is right here. And then I can see that AE, this right here, if this is a 90-degree angle, then this part also must be a 90-degree angle. So it's just 35 plus 90 degrees gets me 125 degrees. Moving on, I can see that the measure of angle AED is a flat semicircle. It's half the circle, so that's 180 degrees. So that's the measure of that arc. And then finally, the measure of arc DEF right here, well, it's 90. And then I have this 30-degree angle on top of that, right? But remember here, I want the length, okay, which is different from the measure. I know that seems weird, but the length. So I got to get the measure first. Well, that's going to be 120 degrees. Then I'm going to divide that by, all right, 360 degrees times 2 pi times the radius, right? And the radius here is 18 meters, right? If you look back here, I told you in the start of the problem that the circle has radius 18 meters. Forgive me for not making that explicit. So just plugging into that formula, when you divide here and multiply, you get 12, and leave it in terms of pi. So don't type pi out as like 3.14, leave it as pi. So this will all simplify to 12 pi meters. All right, let's talk about tangents. So a tangent to a circle is a line in the plane of the circle that intersects the circle at exactly one point, so only one point. So the point where a circle and a tangent intersect, like right here where it intersects at B, is called the point of tangency. So we say that line BA here is the tangent line. BA, the ray, is a tangent ray. And then just the segment BA is a tangent segment. So it just touches the circle at exactly one point. All right, so some radiuses here. So, or theorems, excuse me. So if a line is tangent to a circle, then the line is perpendicular to the radius at the point of tangency. So if this line AB is tangent to circle O right here at point P, then what we can say is the line OP is perpendicular to this line, or excuse me, the segment OP is perpendicular to this line AB. All right, so points of tangency form 90-degree angles is basically what we're saying with a segment to the radius. All right, so let's do a question here. So we have that line or segment ML over here and MN are tangent. Okay, so that means here and here are 90-degree angles. That's what this is saying to the circle. So what is the value of X? Right, we have all these options. We'll look at the shape that's formed. MLON here, right? It's a four-sided shape. So a tangent line is perpendicular to the radius at the point of tangency. The two segments are tangent to the circle, so that means that angles L and N, as I said, are 90-degree angles. Then LM and O is a quadrilateral. So the sum of the angles in a quadrilateral, remember, must be 360 degrees. So if I add up all the measures of this angle, this angle, this angle, and this angle, they must be 360 degrees. Well, it's 90 plus x plus 90 plus 117. If you simplify 90, 90, and 117, you get 297. Subtract that over from 360. And we can say that the measure of angle x, or here, which is the measure of angle m, that unknown x, is 63 degrees. So here, if you look back, the correct answer has got to be B. All right, another one. So the converse of this. If a line in the plane of a circle is perpendicular to the radius at a point, right, then that line is the tangent line. So if you satisfy it in reverse, if we say, hey, this line here forms a 90-degree angle, then what we can say here is that this line is tangent to circle O. All right, so another one. So what is the radius of circle O? So I want to find the radius of X, right? Or this one here as well. Well, how would I find the radius of this circle? Well, here I can see kind of like a triangle. Now here, this side is 12, this side is X, and then the radius, well, from here to here is 8, and from here to here is X. So the radius is X plus 8. So we're going to use the Pythagorean theorem that we've learned. So we have AC here squared is equal to AB squared plus BC squared. So plugging in, remember how I said the radius was X plus 8, so we have to square that. So square this out, you get this. And what you're going to have to do is subtract. So I'm going to subtract the x squareds over, they cancel. 64 over here, all right, gets 80. Divide by 16 both sides, and the radius of this circle is just 5. All right, so two circles in a plane can share a tangent line. So common tangents are lines or segments or rays that are tangent to actually more than one circle. So we have these tangent lines that are tangent to more than a single circle, are called common tangents. So let's look at some of this. So this is the possible intersection of two circles, right, with 2 points of tangent, 2 points of intersection. So they have two common tangents here. If I have circle A, excuse me, and circle B, right, they have two external tangent lines here, like this. How this tangent line touches this one, and this tangent line touches this one and this one here. So two common tangents. Here you see three common tangents, right? So you have two external ones that we've seen, and then one internal one, right, that goes in between the two circles, right? So like you can see that the green ones are on the outside. So when it cuts in between them, we call that an internal tangent. You can see it in black right there. So we have circle A and circle B just touch at this one point of tangency. That's it right there. All right. Another one here, you have a big circle A and a big circle B, and B just touches right here, right? So what we have is we have one common tangent line, right? And that's for two internal tangent circles like this. All right, so let's talk about this. All right, possible intersections of two circles that have no points of intersection. So these guys, as you can see, because they don't intersect at any points here, or even have or even touch at one point here, they can have zero common tangents. So we have two concentric circles, right? So ones that share a common endpoint, and other circles here that do not, or excuse me, share a common center. Here they do not share a common center. So there's no external or internal tangents to this. All right, another one here. All right, we have two circles here that says 4 common tangents. Here they do not intersect, you can see, but they're not inside each other, or one's not inside the other. So you could have a tangent line that crosses here and here, and then those are the external, and then the internal ones that cross between them like this. There's two internal tangent lines. All right, so the line that passes through the center of two circles is called their line of centers. So if two circles are tangent, internally or externally, so see the examples above, right? Then their common points of tangency is on their line of center, right? And these circles are called tangent circles. All right, another theorem, right? So if two tangent segments to a circle share a common endpoint, like here I have this point of tangency, or this line of tangency, and this line of tangency, right, or segments, right, share a common endpoint outside the circle, then the two segments are congruent. So if ray BA, as I said, and ray BC are tangent to circle O, right, then what we can say, and I'm just writing it as rays here, then segment BA to here and segment BC to here to the points of tangency are congruent. All right, so let's do an example. So if AC from here to here and AB, this other line, are tangent to circle D, I want to find the value of X here. Well, remember, if this from here to here is tangent to the circle and here to here is tangent to the circle, and they meet out here, then what we can say, because they share a common endpoint, is that x squared is equal to 10x minus 9. So by that theorem I just said, we know that AC is equal to AB here. So x squared is equal to 10x minus 9. Well, here we're going to have to solve this as a polynomial. So I'm going to move everything over to the other side, like this, and set it equal to 0. Then I'm going to have to factor it. Right? So factoring this trinomial, x squared minus 10x plus 9, it very simply factors into x minus 9, x is equal to 1, x minus 1, and those multiplied equal 0. So using the 0 multiplication property, either x minus 9 or x minus 1 is equal to 0. Solving, you get these two. Now you have to be careful to check, right? But so the value of x is 9 or 1. They'll actually both check out if you plug them in. And this check is just left to you. All right, and a couple more things. So in the figure below, the sides of the triangle are tangent to a circle, like this. So you can see this side, and this side, and this side are all tangent to the circle at one point. The circle is what's called inscribed in the triangle, and the triangle is circumscribed about the circle, right? So inscribed and circumscribed about. All right, so let's do an example. So circle O here is inscribed, remember points of tangency, right? Triangle ABC. What is the perimeter of triangle ABC? Okay. So we can see here, I know what segments AB, AD, and what segments DB are, but I'm missing BE, CE, and AF. Well, remember your theorems here. We can see that segment AD, because of the tangency here, is equal to segment AF. So this is also 10. Following the same idea, BD is equal to BE. So this segment here is 15. And FC is the same as CE. So this segment here is 8. So then the perimeter here, just adding up all these larger segments, right, breaks down into the following. And you can see that it's just 10 plus 15 plus 15 plus 8 plus 8 plus 10, which gets me the perimeter of this triangle is 66.